It's 8 a.m. Pacific time. Let's get started. Good morning, good evening, good afternoon, depending where you join us from. Welcome to today's tinyML talk. I'm Wei Xiao from ARM. I will be your moderator for today's session. The series are made possible by our sponsors, DeepLight, Edge Impulse, Maxim Integrated, Kixel, Reality AI, SynSense, and the strategic partner, ARM. Additional sponsorship available. If you're interested, please email betty@tinyml.org. Two weeks from now, on November 24th, we have another two tinyML talks from ETA Compute and Boon Logic. ETA Compute will introduce how to enable neural network at the low power edge, a neural network compiler for hardware-constrained embedded system. Boon Logic will talk about their Amber solution, a complex ML-based anomaly detection pipeline for microcontrollers. If you want to present in our tinyML web talk series, please email your proposals to talks@tinyml.org. Today is Ehsan Saboori from DeepLight. His topic is networks within networks, novel CNN design space exploration for resource-limited devices. Ehsan is the CTO and co-founder of DeepLight. He obtained his BS degree in artificial intelligence and PhD in computer science. Ehsan co-founded DeepLight, where he assessed emerging challenges for deep learning and formed the technology vision that became the core of DeepLight. So Ehsan, welcome. Thank you for joining us from Montreal.
Thank you. So, yeah, good morning, good afternoon, good evening, based on where you are right now. And first of all, I want to thank you for taking your time today to attend this session. Today, I want to talk about one of the most challenging and annoying problem in deep learning, which is the size of these models. And we want to talk about one of the good approaches to tackle this problem. So before I jump to the problem, maybe it's good to have a quick background why deep learning and why it's a big problem for us. So maybe many of you already know about deep learning and why it's a good thing, and we are hearing a lot about this technology these days. But I think it's a good thing to have few background slides here. So basically, deep learning it's a very powerful tool which helps us to solve lots of tasks. And the reason that it works very well that we have automated feature extraction and it scales very well with the data. So as you can see here, we have a traditional machine learning like a regular or a small fully connected or MLP models, and then we have neural networks, and right now we are in the deep learning era. As you can see here, we can increase the performance, but it comes with a huge cost of number of parameters. So this one cost us, in terms of training, to train these neural networks, which sometimes it becomes super expensive. And also, when you train this model, imagine you have 1 billion parameters, your network becomes like 8 gigabytes. And it becomes hard to deploy it on different or usual commodity hardware. So why we have such a big network, neural networks right now? So basically, when like in 2010 or 11, when people started actually using deep learning in practice and solving problems, it's been a trend to create a deeper and bigger networks over time. As you can see here, it's a very good chart, a famous chart that shows how these models get bigger and bigger over 10 years comparing to hardware. So comparing early days deep learning models and these days deep learning models, the number of parameters it gets, like 300,000 bigger in terms of number of parameters. So it's huge and it's still going. So basically because of that features in deep learning that you can add more parameters, and if you do it in the proper way, you can learn better and better. People start using bigger networks and use more GPUs to train those networks to beat better performance or even human level performance. But on the other hand, hardware, because we are in the like a Moore's law plateau, we can't increase the performance of the hardware. And now we can see there's a huge problem when it comes to running deep learning on commodity hardwares. And the reason that why it's important for us is we can't just use these powerful GPUs, very expensive GPUs everywhere. And we need to find a way to run them on the regular hardwares. That's the intensive for us. And basically we call it edge AI or edge computing. So we have billions of hardwares out there, and they're very tiny, very small, very, very cheap. But the problem here is if your model is like 100 megabytes, 200 megabytes, and you have only 2 megabyte memory on your hardware, how do you want to fit it on the hardware, or how do you want to run it? So for now, it's a big issue in the market and even in academia, how to run these models on these small devices. So if you want to summarize the problems here, imagine you have YOLO, like object detection model, segmentation model, or even classifiers. When you want to run on the edge devices, you have three big challenges. One, when you want to run a model, you have lots of or billions of floating point 32 multiplication, we call it MAG or flops. The other problem here, and they are very expensive for this kind of hardwares. So floating point 32 operations, they are very expensive for CPUs. It is still expensive for GPU, but GPU has been built for that purpose. That's why GPU is very fast for this kind of stuff. The other problem is memory footprint. Again, that's the one of the big problem here. If you have 200 megabyte model and you want to fit it on the 2 megabyte on-chip memory, if you can do it, so you can basically run it. And the other one is the power consumption for sure. So these are the big problems for the edge AI. And in this talk, we want to focus more on the memory footprint. So basically, if you want to tackle memory footprint, you may need to use different techniques. If you want to tackle the first problem, which is the high computational complexity, you may want to use different techniques. But for this call, we want to focus on that, how to shrink a very big network on a very small size. So I think it's good to talk about why it is very important to shrink the network, because we know that you have lots of auxiliary memory on the, imagine Raspberry Pi or this kind of hardware like 2 gigabytes, 4 gigabytes, even 16 gigabytes. So as you can see here, it shows the memory hierarchy in the computer architecture. And basically, it's a very simple concept behind that. When you want to be as close as possible to edge of computing, which is like a registers, flip-flops, it's very expensive, and the capacity is very low. And when you go farther from the CPU or the edge of computing and go to the DRAM, flash memory, or even the hard drive, they become cheap, more capacity, but they become super slow. As you can see here, if you want to put your model on DRAM instead of putting on the cache, the latency goes like 30, 40, or 50 times slower. So it means, forget about the high computational complexity and the other stuff. If you put your model on DRAM, or if you put your model on flash, just this hierarchy of the memory kills the performance by heart. So that's the intuition. That's why we must push the model or the weights and all this information as close as possible to the edge of the computing. So that's why memory footprint is one of the biggest issues here. How to fit that in the, so basically we want to be as much as possible close to the ALU, for example, in the or the top of the triangle. That's why we want to shrink the networks. So this one is like VGG architecture. So basically, it's like a convolutional neural network. We have an input, we have output. So basically, we have different layers. We call it convolutional layers, conv2Ds. We have fully connected layers. We have max pooling, softmax, and maybe ReLU, some activation functions, and other operations. But for now, we want to keep it simple. We can express this model in a different form factor. So as you can see here, we can say we have these layers as a conv layers, where we have pool, fully connected layers, and the output. So that's the way that we usually illustrates a model. So the idea here is how we can make this model smaller. And we want to focus a lot on the compression side. So the idea here is, imagine this layer. It's a big layer. As you can see, we have 512 kernels, 3 by 3. So the idea here is it possible to approximate a part of neural network, a part of that, not everything, and replace it with another neural network, but the other neural network is smaller and thinner? So the idea here is we remove this layer or a part of the network and replace it with a smaller network. So as you can see here, we still preserve the input shape and the output shape of this layer, which is very important because it can help us a lot in terms of maintaining the accuracy. But instead of carrying on 2.3 megabyte, for example, in this example, parameters in this layer, if we break it down into smaller pieces, we will end up with like 140 kilobyte of parameters. It's an example here. We replace this layer with these four layers. And you can see here, we have different numbers, different kernel size here. But the whole idea here is to mimic the behavior of this and approximate that with a smaller, thinner network and just replace it here. So as you can see here, the first step for us is to how approximate or how to build this smaller network. So we can, here I explain two approaches that we can do to replace one layer with 4 or 3 layers. But it is possible to approximate it with different type of layers as well. So let's talk about the transformation function here. As you may know, if you have a 4D tensor, our convolution 2D layers, there are 4D tensors, like input, output, the kernel size, and all this stuff. We can represent the approximate that with this formula. So basically, it's going to be a bunch of separable convolutions. And if you have that one, we can transform this to this formula. So basically, if we have our input x, we can do the forward pass with this formula. As you can see here, we have 4 convolution. And the way that it works, so for the KRS, this one is like a 1 by 1 by S convolution that which we reduce the number of input channel from S to R. So it's like transforming the number, we are reducing the dimensionality here. And then after that, we perform separable convolution in a spatial dimension with this one and this one. And for after that, we have another convolution, which is almost the same as the first one, but here we change the dimension from R to T. As you can see here, that was the original size of the convolution. And it's kind of aligned to our assumption that we must preserve this input shape and output shape. So if we do this, we can replace that layer with this one. But as you can see here, we have 2 important factors here. So what's the size of this shape? You can use any numbers that you want, and it will impact on the size of this small network. Another way that we can see it to replace it with 3 layers, maybe it's better to replace it with 3 layers. And if you want to do it, we can change the way that we see the convolution, and we do the transformation with this formula. And when we go back to this one, we can see that we have a core tensor, which is it does almost all the computation, but the idea is the same here. And we have this convolution KSR3 that it transforms the dimension from S to R3, and then it's like a pointwise convolution. And then we have a regular convolution here, which does the convolution for us. And after that, we have another convolution that it transfer back R4 to T. So basically, it's the same idea here to preserve the shape from the first and the last input and output, but we do the transformation in a different way here. So if we want to see all the steps that how we want to do it, we can see there are some challenges here. So the first challenge here is which layer we want to select. As you can see here, why you don't choose this one or this one or this one or even this one. Also, we can apply the same concept. We can extend it to fully connected layers. So we can still do it on the fully connected layers as well. But the first question that we need to address that which layer you want to choose it. So it's going to be lots of combinations if you want to choose it, right? The other question here is that we need to answer that what kind of transformation function you want to use. Do you want to replace it with 3 layers, 4 layers, even 5 layers? You know, it depends on your preference or your goals. The other one that we need to address that what size you want to use. For sure, we want to go to small enough to be efficient, but we want to be large enough to keep a high approximation accuracy. Because if you use a very, very tiny, small network, it may be hard to approximate the original layer performance. So that's a trade-off here. What's the number there? As you can see here, if you go with 3 layers, you have, you know, like 1 size, 2 size, 3 size, depends on the number of layers that you want to use. And the last part is the approximation part. So basically, when you have your layer, you need to lower the loss to make sure that it approximates enough the original layer that it doesn't drop the accuracy a lot. So these are the 4 steps that we have to do. But the biggest problem, not the problem, the challenge for us that makes the process like exploration problem is to which layer and how to do it. What's the transformation function? What's the size of the network? So they are kind of out of the scope of this call. Maybe we can have another session later to explain more about that part. But that's the part that kind of different from the first part, but it makes it as like a design space exploration problem. So when it becomes exploration problem, it means brute force doesn't work, or you can't just try and error different situation because the space is huge and there's no way to try everything. And you need to find a better way or more learnable approaches to see which one is good for us to break it down to the smaller network and at what size, which impacts directly on the performance of your smaller network. So we have done some experiments, and I want to show some of them here with you guys. So we know that we have different tasks like image classification, object detection, segmentation with different architecture. As you can see here, I just listed some experiments that we have seen and we have done on different architectures and different data sets. And the accuracy changes. So for example, for classification, we have top 1 as accuracy. For object detection, we are using mean average precision, or for the segmentation, we are using mean MIU. So the compression rate, it's varied between like 37x to like 2.4x. And the reason here is when you do the optimization, it really depends on the data set that you have and the architecture that you're using. For example, ImageNet and ResNet50 is one of the most extreme use case here. It's a very, very huge data set, which you need lots of capacity to learn that. And ResNet50 is also a good and big data set. It's like architecture. And we have seen this level of compression, which is in industry is very appealing for them. On the other hand, for example, VGG, we know that VGG is over-parameterized. And C400 data set is not a very complex data set. That's why you don't need that much capacity. And you can see here that it optimizes very well for you. As you can see here, you can see they're like a sponge, and you have to see how much you can compress to preserve the accuracy while you compress it very hard. So, but the most important part is everything here is floating point 32. So it means you can apply some quantization here. Imagine you put like 4x, you can go like 80, 20, 30, 10, or 15x reduction in size. And the other thing which is very important that I have to mention here that we have observed, and it is very, very cool, that as you can see here, we optimize ResNet 50, the original one, and we have ResNet 50 optimized version here. As you can see, it's a very important takeaway here. The optimized version of ResNet 50 works much better than ResNet 18 on ImageNet. As you can see here, it's smaller, less flops, and less number of parameters. As you can see, we have almost 5% more accuracy, which is huge in ImageNet. Even for ResNet 34, it is still better than that. So we have seen it even in the C400 data set. If you take ResNet 18, which is a big model for C400, when we compress that, we obtain much better performance than MobileNet. And we know that these kind of models like MobileNet, ShuffleNet, they are very handcrafted, extreme compact models that people actually train them, build them. If we go to the VOC data set, we can also see the same trend. We have MobileNet V2 SSD Lite, one of the most extreme object detection model out there. And we have MobileNet based SSD, ResNet 50 SSD, and YOLO. YOLO, we know that YOLO has a very good accuracy, but it's very, very big and very, very slow if you want to run it. But for this purpose, we optimize YOLO V3 with good amount of accuracy drop to see what we can achieve if we push very hard for compression. And as you can see here, this model easily beats this model. So we have a better performance, we have almost a smaller network, and here it kind of shows the way that why we can't just use a large network, because we know that if you have a very large network, it's easier to train a large network. And when you train your large network, just compress it. And you can, most of the time, you can have a better performance and you beat these extreme compact models. So that's the one of the approaches that we are using also besides other techniques as well. But of course, if you want to go for MCUs, you need to tackle the computation problem, because again, they are floating point 32 models. If you want to run them on MCUs, you need to quantize them. And there are other challenges there that we need to tackle. But it's a one good approach that if you want to compress your neural networks, it works very well as long as you can solve that exploration problem. So I would thank you so much. And if there's any question, I would be more than happy to answer.
Sure, thank you, Ehsan.
No worries.
We have a couple of questions from our audience.
Sure.
First one, so the result looks great. Do you know how the compression affects real-world performance?
Good. That's a good question. So I think it's a very, we have another task right now. We are working on that as our R&D question, that what's the difference if you have a compact model? Because it becomes a new model. And we have seen that in some cases, it outperformed the original model in some use cases. And sometimes it doesn't work as good as the original model. So it becomes an open-ended question that we need to work on that. So to see how to compare them, because again, it's a new model and it works almost the same on the same data set, but when it comes to the unseen data, in most scenarios, it works better. In some scenarios, it works the same, and some scenarios, it works worse. But it's a one thing that we have to figure out or define the way that we want to compare these models. But at least on the same test data set or valid data set, it works the same. And in most scenarios, even it works better. Because if you can see the optimization problem as like a regularization. You remove lots of redundancy from the network, and your smaller network, in most scenarios, it learns better because it has the most efficient information in that small, compact model.
Cool. Our next question is,
Sure.
oh, somebody is asking, do you have this published as a paper?
We are working on that. As soon as we publish that, we announce it on the LinkedIn or our website.
Great. Next question, what's the disadvantage to replacing a layer with a smaller one?
Disadvantage, so basically one thing that we have to consider here, because we add more layers, maybe the latency goes up. But they are thinner, so it means it can kind of compensate that effect. But at the end of the day, you have more layers, and it means the latency may go up on like GPUs. But the whole point of this technique is to make sure that you can fit the model on the on-chip memory. So that's the disadvantage.
Okay. Next question, have you tried this on EfficientNet?
That's going to be the one that we are going to do. We have done it on MobileNet, we have done it on Google Net, DenseNet, but efficient is one thing that is in our to-do list.
Okay.
Yeah.
Does the compression procedure require a collaboration data set?
No, basically we use the same data set as the original data set.
Okay. So our next question, how is the compression results and the performance of this approach as compared to the knowledge distillation approaches? Which is better for model compression?
So, we are also using knowledge distillation in this process to distill the knowledge from teacher. But at the end of the day, knowledge distillation itself alone doesn't help you to compress, because you need to define or design your student and then use knowledge distillation to put the knowledge in the student. But the idea here is, what's your student? And this way, if you do the proper exploration, you can define your student and then use knowledge distillation to train the optimized model. So I would say they're a bit different, but we can use knowledge distillation with this approach.
Thank you. We only have time for one more question.
Sure.
Could this technique be applied to audio sequence models?
Maybe. We haven't tried that, but as long as this is, if your model is a CNN-based model, yes, we can apply that. But if your model is like RNN models or different type of models, we haven't tried that yet.
Okay. So yeah, we still have a couple of questions we don't have time to address. We will post these open questions to our tinyML forum, and Ehsan will help you answer them afterwards.
Awesome.
Yeah,
sure.
Thank you very much for your presentation.
Thank you so much.
Today. So again, thanks to our sponsors to make this series possible. Yeah, I'm pleased to announce that ARM becomes tinyML's strategic partner. ARM designs a family of Cortex-M microcontrollers and Ethos-U, excuse me, micro NPUs for tinyML applications. A couple of weeks ago, we just announced our second generation micro NPU Ethos U65 for accelerated tinyML applications. DeepLight uses AI to make other AI faster, smaller, and more power efficient. Edge Impulse offers online tinyML lifecycle solutions, which transform developers' abilities to deploy machine learning for embedded devices. Maxim Integrated enables edge intelligence with their sensors and signal conditioning technologies. Kixel AutoML platform builds tinyML solutions for the edge using sensor data. Reality AI offers optimized feature discovery, compact embedded code, optimization toolkit, and tools for managing the cost of data collection. SyncSense builds ultra-low power sensing and inference hardware for embedded, mobile, and edge devices. So 2 weeks from now, on November 24th, 8 a.m. Pacific time, we will have presentations from ETA Compute and Boon Logic. Please join us then. Our first APAC event, tinyML Asia, is going to take place next week between November 16th to 19th. The event is free to our audience, thanks to our sponsors. Don't miss the opportunity to sponsor or participate in the event. Thank you all for your time and attention. We look forward to seeing you again in the next tinyML Web Talk.